This is part 4 of lecture 6 of Applied Machine Learning. In the previous videos, we saw our first supervised learning classification algorithm, which was called nearest neighbors here. In this video, we are going to see a new supervised learning classification algorithm called logistic regression. And logistic regression will address many of the limitations that nearest neighbors has. And it's also going to be an example of a parametric approach to classification. And more generally, logistic regression is a very important algorithm. It's one of the most important algorithms in supervised learning, and it's something that should be part of every person's toolbox. So let's start by reminding ourselves about the definition of classification. In classification, we have, or more generally in supervised learning, we have a data set, a training data set of this form. And if the targets y are discrete, if they take one of a finite number of possible classes, then we call this a classification problem. And specifically, if the number of classes equals to 2, we call this binary classification. And in this video, we are going to focus only on binary classification, and we will see that logistic regression is an algorithm that is aimed specifically at binary classification. And then in the next video, we will see how we can extend logistic regression to a general number of classes. And as a running example, we will again use our iris flower dataset. I'm going to load this dataset here, but we have seen it in earlier videos. Essentially, this is a dataset where each point here visualized in 2D is a flower. And for this flower, we have collected a number of measurements, such as the petal length or the petal width. And here I have projected this data set along these two dimensions, which are along these two measurements, which are collected for every flower. And in this data set, we have 3 types of flowers, but for the purposes of this video, I am going to merge the 2 non-setosa types of flowers. So we're going to be classifying iris setosa versus non-iris setosa. And you can see the 2 classes here in different colors, blue and brown. These are blue is setosa, brown is non-setosa. And our goal is going to be to learn to distinguish between these 2 types of flowers. Now, one way in which we could solve this problem, potentially, and also using a parametric approach, would be using least squares. Recall that our least squares model assumes a supervised learning model of the following form, where f is a linear function of inputs x and parameters theta. And we fit this model using the mean squared error, which involves solving the following optimization problem, where we're minimizing the distance between the prediction given by our model, which is here, and the true target, which is on this side. So if this data set is a supervised learning data set, is a supervised learning classification data set, then each y here is a binary target, if this is binary classification. And this is a valid approach because we're simply training our model to output a training data point, to output a prediction for this training data point, which matches the 0 or 1 label. So in theory, we could view this as a purely regression problem. In fact, we can try to solve this problem by importing our linear regression model from scikit-learn and training it on this data set of iris flowers. And we can visualize the results of this algorithm, and indeed by running linear regression, we obtain some separation between the 2 classes, which looks reasonable. So here, this is a line that we have learned by fitting a linear regression model of the kind that we saw earlier in the previous lectures. So this approach returns a boundary which looks reasonable, but it's also problematic for a few reasons. First of all, there is nothing to prevent the outputs of our model, which is f, which is simply theta dot product with x. There is nothing to force these outputs to output labels that are either that are close to 0 or 1. our model can output something that's greater than 1, that's less than 0, and this is just conceptually wrong because we know that the only two classes, the only two labels that we have are 0 and 1. So conceptually, it's not a very elegant approach. And in practice, this problem, this approach doesn't give us the best possible performance. If you just look at this example here, we have a hyperplane which separates the two classes, but this point here is misclassified, and these 2 points are very close to the boundary. So this is not the optimal solution. And in practice, the fact that we're trying to use this regression algorithm, which assumes a general type of y, and we're trying to apply this to a problem where y is either 0 or 1, this is conceptually wrong, and it also introduces errors in the data set that we find, the errors in the boundary that we find, and it just doesn't return us the best possible solution. So in practice, this is not the best thing that we can do. In this video, we're going to look at a different kind of model F that connects inputs and targets. And this model will have the following form. Here, our model F is going to be a function sigma of theta transpose x. So what you see here, theta transpose x is our linear model, and now we are going to feed the output of this linear model into this function called the sigmoid or logistic function, which has this form. I'm going to explain in a second what this function does, but if we combine this function with the definition of our model, we have a model that takes the following form here. This is going to be the model family that we're going to consider. Okay, so we're going to assume that we're working with models that have this particular type. Now we can better understand why we chose this particular form by visualizing the logistic function. So the logistic function, it maps the real numbers into the interval between 0 and 1. So it squeezes points from the real line into the unit interval between 0 and 1. And we can define this function in Python, and we can visualize it here between -5 and 5, and it takes the following form. It looks a little bit like the letter S, which is why it's also called the sigmoid function, or it's also known as the logistic function. And you can see here that when the input to the sigmoid function is 0, it outputs 0.5, and then as we approach the value infinity, we approach so the value of the sigmoid increases, and then it asymptotically approaches 1 as the input z goes to infinity, and conversely it approaches 0 as z goes to -infinity. So here we're squeezing all the possible values on the real number, on the real line, into a number between 0 and 1. And this is intuitively what we want, because we have two classes denoted by 0 and 1, and we want to output something that's between 0 and 1, and if the output is not 0 or 1 exactly, we can interpret it as a probability or as a confidence measure of how close we are to 0 and 1. So for example, if our model would output 0.5, then we would say that we're equally confident between the two classes. If we were to output 0.9, then we think that it's most likely the class 1. So squeezing the numbers between 0 and 1 is something that's really reasonable for a binary classification problem. We can I'm going to describe here a few additional properties of the logistic function. I mentioned this earlier, but again, it tends to 1 as its input goes to infinity and 0 as it goes to -infinity, which makes the values between 0 and 1. And it's also easy to derive a derivative for this function, and you can check yourself by using calculus that the derivative of this function has the following convenient form. So the derivative of sigma is sigma times 1 minus sigma. All right, and now we can use the sigmoid function to implement a model f. So this is a model that takes an input x and a parameter set theta, and now the output of the model is simply sigmoid times theta dot product with x. So we have defined so far our supervised learning model. Now our goal here is to define a supervised learning algorithm, and therefore we still need to define an objective function over the set of all the possible models that we in the class that we have just defined, and then we have to define a way of optimizing this objective in order to find the best fit, the best model within the class according to our objective. So what objective would be appropriate for this model class that we have just defined? In order to define an objective, we're going to follow the probabilistic approach to classification, which we have discussed in the previous lecture. So we're going to start by giving a probabilistic interpretation to our algorithm, and then we're going to apply the principle of maximum likelihood to derive an objective. So we can interpret, and I just alluded to this earlier, we can interpret the output of our model f. So we can interpret sigma of theta transpose x as a probability. Because it's between 0 and 1, we can interpret this number as the probability that the class is 1 according to our model, and then conversely the probability of it being 0 is simply going to be 1 minus theta, 1 minus the sigmoid function, so 1 minus the output of the model. So here I have assigned a probabilistic interpretation to our model, or in other words, I have now defined a probabilistic model which has this form here on the right that is specified by the function I just defined earlier. And we can also think of this as parameterizing what is called a Bernoulli distribution. So a Bernoulli distribution is simply a probability over a variable that takes two outcomes, and this probability distribution has the following form. It has a single parameter p, and now we are simply parameterizing p as this particular via this particular expression. And if you watched the videos from lecture 5b, you saw that we took a similar approach to define a probabilistic interpretation of the Gaussian to define a probabilistic interpretation for least squares by parameterizing the mean of a Gaussian distribution. Here, in the same way, we're parameterizing the one parameter of a Bernoulli distribution. All right, so now we have defined the following probabilistic model, and we can also write this model a little bit more compactly in this form. Since y is either 0 or 1, we can write it in this form, and if y equals 0, well, here we have something to the power of 0 that's 1, and here this is to the power of 1, so we have we essentially recover our definition. This is just a bit of a convenient notation. And now that we have a definition of a probabilistic model, we can apply the principle of conditional maximum likelihood to obtain an objective for this model. So recall that the definition of conditional maximum likelihood is the following objective, where we are choosing a set of parameters theta such that samples xy from the data distribution have high probability. And optimizing this objective, maximizing this objective, is equivalent to minimizing the expected KL divergence between the distribution over y that's given by our model relative to the distribution over y that's specified by the unknown data distribution. So this is a very general objective that is interesting for many reasons, in addition to optimizing the scale divergence. And so we are going to use this objective as our objective for training our model that we have just defined. So if we apply the principle of maximum likelihood, we obtain the following objective. We obtain the following likelihood, which is, so given a data set D, this is simply the probability of each y given x under our model. And now here I'm just plugging in the definition of the model that we have given earlier, and we obtain the following objective. We're going to be working with the log of this objective, and in that case, It is also known as either the log loss or the cross entropy objective. So together, this model and objective, and I will define the optimizer in a second, but it's going to be gradient descent. And this model and objective function, they define an algorithm called logistic regression, which is one of the most widely used classification algorithms. Now, this is important to note that even though the algorithm is called logistic regression, this is a misnomer. It is not a regression algorithm. It is actually a classification algorithm, and it's an unfortunate historical fact that this algorithm ended up being called logistic regression. It is an instance of regression if you invert the sigma and you're fitting if you apply the inverse of sigma on both sides of this classification problem, then you might have something which looks more like a regression problem. This is not really important. We should just remember that logistic regression is a classification algorithm. So we can implement this objective very easily in Python. Here, this is the log likelihood, and it has the following form here, which is simply applying the definition that we saw earlier and implementing it in Python. Now, as I mentioned earlier, in order to optimize this objective, we're going to use gradient descent, which is a general purpose optimization algorithm that we saw earlier. And you may recall that the definition of gradient descent consists in repeatedly applying the following rule. So here, if we're minimizing j, we are going to be applying the following function where we repeatedly take steps in the direction of steepest descent as specified by the gradient j. And if we implement this in pseudocode, then we have something which looks like this. This looks very much like Python. So we repeatedly move in the direction of steepest descent as specified by the gradient. And in order to apply the principle of, in order to optimize the log likelihood, we need to compute the gradient of this objective. And in order to compute the gradient, we need to compute the partial derivatives. So recall that the gradient is the vector of partial derivatives, and now we need to compute a form for each partial derivative of the log likelihood. So you can convince yourself that the log likelihood has the following form. Here in the first line, I have simply used the definition. Now here I have used the definition of the log to make this a sum of two terms. And now taking the derivative of these two terms, we have the following expression, which is maximized by what was inside the term, which is this thing here. Now in this line, I am applying the definition of the gradient of logistic regression, which I showed you on the earlier slide, and we still have to multiply by here. This is theta x here on this side, and now taking the final derivative, we have this form. So this is now, this line here now looks like the definition of our gradient, except that we can also make this a little bit simpler by, again, using the fact that y is either 1 or 0, and the fact that the output of our model is this expression. You can convince yourself that when y equals 1, well, this term is 0, and now we have 1 minus the output of the model, so we have this form. And similarly, when y equals 0, then we only have this term, and this again looks like the following expression. So if you work through this math, you will see that the gradient, the partial derivative has the following form. And now we can combine all of these partial derivatives to obtain the gradient, which will have the following form that you see here. And it's interesting that this expression has a really similar form to the gradient of the mean squared error that we saw. There again, we had the difference between y and f times the vector times the input x. This was our gradient too. But even though it has a similar form, this is actually a different. This is going to be a different. It will take a different value because the function f here that we're using is different. If we're optimizing for logistic regression, f is going to be a logistic regression instead of a linear model. But it's interesting that it has a similar form, and there is in fact a theory which we will not be covering here, but there's a theory of what are called generalized linear models, which can explain why the form remains the same. But for now, this is just an interesting observation. And again, there's also an intuitive interpretation for why we would have this term here, because we are interested in minimizing the difference between y and the output. So it's normal that we're scaling by this difference. Again, we can easily implement this gradient in Python. This is, again, very short. We're using NumPy to implement this in one line of code. And now plugging in this into our definition of gradient descent, we have the following expression. And now we can also implement this algorithm very easily in Python. So here I have essentially just re-implemented the pseudocode from the previous slide, and I have also added a few extra lines of code to store the gradients and the optimization points and to print out progress. And now if I were to run this, I am going to be optimizing the log likelihood over a number of iterations. And as we train, the log likelihood increases because we're maximizing it. And in the end, after a number of iterations, we have the output of logistic. We have attained the maximum set of weights. And now in this figure, I'm visualizing the output that was found by logistic regression, and it is simply the line that you see here between the blue and the brown regions. So logistic regression has found this linear decision boundary between the two classes, and we are assigning the points in this area as being of class. I think this is one class and blue is the other class. And now we have perfectly separated these two classes. This point here is correctly classified, and so now we have. You can also see that this solution is better than what we have found using linear regression. We're able to perfectly separate the two classes. I will make a few observations about logistic regression. One observation that I would like to make is that the fact that the decision boundary was linear is not a coincidence. Logistic regression is still an algorithm that finds a linear decision boundary between the two regions, and we can convince ourselves that this is the case by visualizing this via the following expression. So here I have the ratio of the two classes, and at the boundary this ratio is equal. And then if we work out the math, well, this is unfortunately my slides are a little bit cut off here, but this is going to be theta transpose x, and this is simply this is going to be a linear function. So this ratio is going to be of the two probabilities is going to be a linear function, which means that our boundary is linear. Now, the other important distinction is, unlike least squares, which we saw earlier, we do not have a closed form solution for the weights theta. So with a least squares model, we were able to optimize our mean squared error objective directly in closed form, and we had a closed form expression for the optimum that we obtained via the normal equations. We no longer have this closed form solution for logistic regression, which is why we have to optimize it numerically using gradient descent. And this is the example that you saw earlier. So summarizing what we saw in this video, we saw logistic regression, which is a type of supervised learning, and that is applicable for binary classification. Again, regression is an unfortunate misnomer. This is actually a classification algorithm. And we're looking at the model families, which consists of linear decision boundaries between the two regions. And we're training this using maximum likelihood, which in this case is also called the cross entropy. We're optimizing this using gradient descent, and we can view this from a probabilistic perspective as fitting an approximation to a parameterized Bernoulli distribution. In the next video, we're going to see how we can extend logistic regression to multiple classes.